Installing a standby generator at a pumping facility requires careful consideration of grounding requirements, particularly in a three-phase, three-wire system. The National Electrical Code, commonly referred to as the NEC, mandates that generators must be grounded to ensure the safety of both personnel and equipment. This grounding provides a low-resistance path to ground for fault currents, which is essential for proper operation of overcurrent protection devices like circuit breakers and fuses. In a typical three-phase, four-wire system, the neutral conductor is connected to the system's grounding electrode system, providing this necessary path. However, in a three-phase, three-wire system, the neutral conductor is absent, which complicates the grounding process. Omitting the generator's grounding would violate the NEC. Firstly, let's discuss why grounding is so important. Grounding provides a reference point of 0 volts potential. This means that any unintentional contact between a live conductor and a grounded surface will create a fault current. This fault current will then flow back to the source through the grounding path, tripping a circuit breaker or blowing a fuse and de-energizing the circuit, thus preventing electrical shock or fire hazards. Without proper grounding, a fault could cause a metallic enclosure to become energized, posing a significant safety risk. Secondly, grounding helps to reduce electrical noise and interference. This is particularly important for sensitive electronic equipment that may be connected to the system. A properly grounded system provides a stable reference point, minimizing voltage fluctuations and unwanted signals. Thirdly, grounding is crucial for the proper operation of surge protection devices. These devices, such as surge suppressors, divert high-voltage surges to ground, protecting equipment from damage. Without a proper grounding path, surge protection devices cannot function effectively. Given that the existing utility feed is a three-phase, three-wire, 480-volt system, there are several ways to address the grounding requirement when installing a 60 kW generator. One approach is to install a three-phase, four-wire transformer. This transformer would take the three-phase, three-wire, 480 volts input and output a three-phase, four-wire, 480-volt system, providing a neutral conductor. This new neutral conductor can then be connected to the generator's neutral and the grounding electrode system. The grounding electrode system typically consists of ground rods, a metal underground water pipe, or a concrete encased electrode, all bonded together to form a low-impedance path to earth. The generator's neutral should be bonded to the transformer's neutral at a single point to prevent circulating currents. Another option involves using a three-phase, three-wire transfer switch with a neutral bonding provision. This type of transfer switch allows the generator's neutral to be bonded to the system's grounding electrode system only when the generator is running. When the utility power is present, the neutral connection is automatically switched back to the utility's neutral. This prevents paralleling the generator neutral with the utility neutral, which can cause ground loop currents and other problems. However, it is crucial to verify that this approach meets the requirements of the NEC and any local electrical codes. The NEC generally does not allow the use of a three-phase, three-wire transfer switch for a generator without proper grounding. Therefore, it may be necessary to obtain a variance, which is a written permission from the local electrical inspector to use this option. Obtaining a variance typically requires demonstrating that the proposed installation meets the intent of the code and provides an equivalent level of safety. The NEC specifies requirements for grounding and bonding in Article 250. This article provides detailed information on grounding electrode systems, equipment grounding conductors, and bonding jumpers. It is essential to consult Article 250 to ensure that the generator installation complies with all applicable requirements. For example, Section 250.20 covers general requirements for grounding of electrical systems, stating that alternating current systems operating at 50 volts or more must be grounded. Section 250.30 provides specific requirements for grounding separately derived systems, such as generators. This section requires that the neutral point of the generator be connected to a grounding electrode system. Section 250.50 details the requirements for the grounding electrode system, specifying the types of electrodes that are permitted and how they must be installed. Section 250.104 covers bonding of metal water piping systems and other metal structures. This section requires that these metal structures be bonded to the grounding electrode system to prevent them from becoming energized in the event of a fault. When installing a generator, it is important to consider the size of the grounding conductors. The size of the grounding conductor must be based on the size of the generator's overcurrent protection device. Table 250.122 in the NEC provides guidance on selecting the appropriate size of grounding conductors. For example, if the generator has a 100 amps overcurrent protection device, the grounding conductor must be at least number 8 American wire gauge copper. The grounding conductor must be run in the same raceway or cable as the circuit conductors. The grounding conductor must be connected to the generator's neutral terminal and to the grounding electrode system. In addition to the grounding conductor, it is also important to install a bonding jumper between the generator frame and the grounding electrode system. This bonding jumper provides a lower impedance path for fault currents to flow back to the source. The size of the bonding jumper must be based on the size of the generator's overcurrent protection device. Table 250.102 in the NEC provides guidance on selecting the appropriate size of bonding jumpers. For example, if the generator has a 100 amps overcurrent protection device, the bonding jumper must be at least number 8 American wire gauge copper. When selecting a transfer switch, it is important to choose one that is properly rated for the generator's output. The transfer switch must be able to handle the generator's full load current without overheating. The transfer switch must also be listed by a recognized testing laboratory, such as Underwriters Laboratories or Intertek. The transfer switch must be installed in accordance with the manufacturer's instructions and the NEC. When installing a transformer, it is important to choose one that is properly sized for the generator's output. The transformer must be able to handle the generator's full load current without overheating. The transformer must also be listed by a recognized testing laboratory. The transformer must be installed in accordance with the manufacturer's instructions and the NEC. It is crucial to consult with a qualified electrical engineer or licensed electrician to ensure that the generator installation complies with all applicable codes and standards. They can assess the specific requirements of the installation and recommend the best solution for grounding the generator. If the generator is located outdoors, it is important to protect it from the elements. The generator should be installed in a weatherproof enclosure to prevent damage from rain, snow, and ice. The enclosure should also be ventilated to prevent overheating. The generator should be installed on a concrete pad or other solid surface to prevent it from sinking into the ground. If the generator is located indoors, it is important to provide adequate ventilation. The generator should be installed in a well-ventilated room to prevent the buildup of exhaust fumes. The generator should be installed away from flammable materials. It is also important to install a carbon monoxide detector in the room where the generator is located. Regular maintenance is essential for ensuring the reliable operation of the generator. The generator should be inspected regularly for any signs of damage or wear. The oil should be changed regularly, and the air filter should be cleaned or replaced as needed. The spark plugs should be inspected and replaced as needed. The battery should be checked and charged regularly. The generator should be tested regularly to ensure that it is functioning properly. In summary, grounding the generator in the three-phase, three-wire system is essential for safety and code compliance. While modifying this system with a three-phase, four-wire transformer is a reliable solution, using a three-phase, three-wire transfer switch with a neutral bonding provision may be an option, but requires careful consideration and potential variance approval. Always consult with a qualified electrical professional to ensure a safe and compliant installation. Furthermore, consider the specific application and load requirements when selecting the appropriate grounding method. Motor loads, for instance, can generate harmonic currents that can affect grounding performance. A properly designed grounding system will minimize the impact of these harmonic currents. Also, consider the potential for future expansion of the electrical system. If there is a possibility that the system will be upgraded to a three-phase, four-wire system in the future, it may be beneficial to install a 3-phase, 4-wire transformer now to avoid the need for future modifications. The cost of each option should also be taken into account. Installing a 3-phase, 4-wire transformer is typically more expensive than using a 3-phase, 3-wire transfer switch with a neutral bonding provision. However, the transformer provides a more robust and reliable grounding solution. The cost of obtaining a variance should also be considered. The cost of a variance can vary depending on the local electrical inspector and the complexity of the installation. Ultimately, the decision of which grounding method to use should be based on a careful evaluation of all of the factors involved. This includes the NEC requirements, the specific application and load requirements, the potential for future expansion, and the cost of each option. Always prioritize safety and code compliance when making this decision. Remember that electrical work can be dangerous, and it is important to take all necessary precautions. Always to energize the circuit before working on any electrical equipment. Wear appropriate personal protective equipment, such as safety glasses and gloves. If you are not comfortable working on electrical equipment, it is best to hire a qualified electrical professional.